Hi, so today we're going to talk about the math basics that you need for chemistry and some scientific notation. First, we're going to mention place values, how to read an instrument in lab, and some rounding rules. Then we're going to go into order of operations, an algebra review, and exponents and scientific notation. And if you need more help, there is a great YouTube playlist by content creator Melissa Maribel. She does a lot of really good chemistry videos with different topics that we will encounter in this class. She also goes through a few more advanced things, so be careful when you're looking through her videos to make sure that you don't need that information, because sometimes she does go into a little more advanced detail than you need for this class. So we're going to get started with place values. So let's say I have a number. We don't need to go that far, actually. Let's put the decimal here. Okay, so each of these numbers has a place value, and you need to recall the name of that place value because I'm going to use that terminology when we talk about rounding and when we talk about reading instruments in the lab. So let's label these place values. First, the 1 is in the thousands place. Murphy, hush, sorry. Murphy has thoughts. The one is in the thousands place. The 0 is in the hundreds place. The 7 is in the tens place. And the 3 is in the ones place. Now you can tell based on how far away these numbers are from the left of the decimal. If you do not have a decimal and we just had the number 1073, we would just assume the decimal is at the end and these would all remain the same place values we have assigned. Now let's go and look at the ones we're probably going to encounter more with questions about where do we stop with rounding and where do we stop with reading instruments in the lab. The first one to the right of the decimal is the tenths place with a TH on the end. The next one is the hundredths place with a TH on the end. And this one here would be the thousandths place. Now, on the other side of thousands, you have 10 thousandths, 100 thousandths, millionths, but we're not going to go into that much detail with naming these. But I will say in lab, or you will hear in lab, oh, make sure you're rounding to this instrument is marked to the tenths place, or we need to make sure we're rounding to the hundredths place or the ones place, and you need to know what place that is. So make sure that you can identify what place everything is. So let's look at how to read an instrument in lab. And we'll probably talk about this more in lab, or you will talk about this when you're in lab if you have a different instructor for lab. But it's really important to be able to read every instrument that you encounter in the lab. And a lot of times students feel like, oh, well, I can read a ruler, I can read a graduated cylinder. However, I wind up, when I'm grading lab reports, taking the most points off for some of these simple things that we think we know how to do, but maybe haven't been taught explicitly what to do here or have forgotten. because it might have been a long time for some of us to really remember how to read things. So the general rule that you can remember is to read one place after the marking. And that doesn't make a whole lot of sense just looking at the words here, but let's look at an example. So if I'm trying to read the length of this bar, and let's say I have a ruler, say my ruler starts here, and then it cuts off over here. So this is my ruler, and the markings are at 1, 2, 3, 4, 5. We'll put in a 6 here. So let's look at which place it's marked to and which place we're going to read it then. So the marked place, it has markings at a place. And we can think about asking yourself, well, how do I know where it's marked to? Well, every little tick mark is going to be adding or subtracting something. So as I go from 3 to 4, I'm adding 1. So it's marked to the ones place, right? If I were to go from 3 to 2, it would be subtracting 1. So it's marked to the ones place. Every tick mark represents 1, a ones place. So this is marked to the ones place. So if it's marked to the ones place, let's think about where we're going to read the recording. The rule is to read the recording one place after. When I say after, I mean to the right of. So being very explicit here. If this is the ones place, the number that comes after the ones place is the tenths place. Yes, I know the decimal is technically what comes after the ones place, but that's not a place in itself. It's not a value. It's just a marker. So the next value after the ones place is the tenths place. So it's marked to the ones place. We read to the tenths place. So I could look at this and say, well, I think that's like 4 point something. And we can argue about what that is. It could be 7, it could be 8, it could be 6, and it doesn't matter. That's what we're guessing. So the last place that we write down is the one we're guessing. Nobody's arguing that this is in between 4 and 5. So we're pretty sure that's a 4 there. But we don't really know what the next number is because we're kind of guessing in between 4 and 5. So let's look at another example really quick. Let me just shortcut this and bring my ruler over. Let's use the same ruler. But now let me make this sit right on the line for 3. Now, if I think this is right in line with 3, the correct reading would not be 3 because the last number we say is the number we're guessing. I'm not guessing the 3. It's marked on the 3. I'm guessing what comes after the 3. So even if it's right on a line, we have to say 3 point what? This could be 3.0 if maybe you think it's 3.1. maybe you think this is 2.9, right? But if you think it's right on the line, then 3.0 is probably a good option for thinking something is right on the line. But every reading on this ruler that is marked to the ones place will have a reading to the 10th place. Every reading, even if it's on a line. So don't forget that once you establish what decimal place you're using for your instrument, every reading on that instrument goes to that same decimal place. So let's write that down. Every reading on an instrument goes to the same decimal place. So if you're not sure how to read something that's right on a line, just ask yourself, well, what would it be if it were in between lines? Then that'll tell you how many decimal places that you need to have. You'll have a lot more practice with this in lab, and you'll have a lot more practice with this. There's practice in the text as well. Okay. Next up is rounding rules. So rounding rules are, we're going to keep them very simple. You may have encountered rounding rules before that were more complicated with what to do with fives. Mathematically, the more complicated 5 rounding rule is correct, but we're just going to keep it very simple in this class. And if your instructor in a future class wants you to do something different, then of course adhere to the rule that they want you to have. But we're going to just use a simple rounding rule here. So we're going to round up if the number after the place we want is 5 or greater. But only one number. We're only looking at the next number after we want to stop. We're not looking at multiple numbers. You're going to round down if the number after the place you want is 4 or less. So let's look at an example. If I said round to the 10th place, think about what you would put. So if we're rounding to the 10th place, oops, don't want to confuse you with those colors. Let's look at the number. Just going to rewrite the whole number here. What's the 10th place? The 10th place is here. This is the 10th place that we want, the 3. So we're going to cut it off after that number. So we look to the number that's to the right of the 3. You're not looking at the 9 or the 2. You're only looking at the 4. Is this greater than or equal to 5? No. So we're going to leave it down. Oop, and I said round down here. What I mean by round down is leave it alone. Apologize. Leave it alone. So we're not going to round it down. I think we use that language sometimes, rounding down to decrease the number, but what I mean is you're just going to keep it the same. So our answer here will be 1.3. Okay, if we took this same number and we said round to the hundredths place. The hundredths place is this 4. The number to the right of the 4 is a 9, which is greater than 5. So we're going to round that up. So we're going to turn the 4 into a 5. Sometimes you may have to round a little bit more than you think, or might be kind of confusing rounding. So let's say, what if this 2 on the end was a 5? And I said round to the thousandths place. So the thousandths place is the 9. The number that comes after it is a 5. So we need to round the 9 up, but we can't turn it into a 10 because it has to stay in that same place value. So I want you to think about the number, back it up a little bit. Instead of this being a 9, think about this being a 49. And how do we round up 49? We say 50. So we can turn the 49 into a 50. And that would be how to round up something that has a 9 on the end. Just back it up a little bit and think about the number a little bit larger. Instead of 4 and then 9, think about 49, and that can be helpful to figure out what to do, because we will have to change that previous number. We're going to change the 4 as well as the 9. So let me know if you have questions about any of this stuff when you come into class or via text, email, etc. Okay. Quickly moving on to order of operations. We're going to cover this next part pretty quickly. Again, I'm hoping that this is just a review for you. So the basic order of operations is PEMDAS. And what a lot of people don't understand about PEMDAS is that each pair is actually equal. They forget this. So powers, parentheses, and exponents are on the same level of order. Multiplication and division are on the same level of order. And addition, subtraction are on the same level of order. So when you get to those things, you just have to do them left to right, top to bottom, in the order in which they're written, because they're actually the same. So if I gave you like 3 plus 7 minus 2, you wouldn't do the 7 minus 2 first. These are all the same order. They're all in the same order of operation. It's not addition first and the subtraction. It's just whatever comes first, reading left to right. So we would do 3 plus 7, which is 10, minus 2, which is 8. If we had 3 minus 2 plus 7, it's not going to be 2 plus 7 minus 3. It's going to be, just read it left to right. 3 minus 2 is 1, plus 7 which is 8. So when you get into addition versus subtraction, multiplication versus division, parentheses versus exponents, they're the same order. You just do them left to right how they're written. So repeating really quickly, I'm not going to write it out because you probably know this, but if you want to pause and write it out, you can. This is parentheses and exponents come first, then multiplication division comes next, then addition subtraction comes last. So if you want somebody to do addition subtraction before multiplication division, you'd have to put the addition subtraction in parentheses, and that would mean that it would be a higher order of operations. Okay, let's talk about negative numbers because I consistently have students of all levels that don't always recognize that negative numbers are not quite as difficult as I think they are. So for example, 3 minus 2 is the same as 3 plus negative 2. Subtraction is just the addition of a negative. And so when I give you something like, you're doing algebra and you're plugging in like a negative 2 here for 3 plus something, it's really just 3 minus 2. Okay, a subtraction is just an addition of a negative. And you can think about it on a number line. I don't actually want to put brackets on it. You think about it as a number line. If I start here at 3 and I take away 2, I'm going to be going in the reverse direction, 1, 2. So that would be equal 1. If I take 3 and I add negative 2, it's still adding a negative. So we're adding another negative and we go backwards. So it's the same direction on the number line, which means they're essentially the same. Another thing that I think students run into is this issue of subtracting negatives. So if I have, let me not do 3 because I'm going to run out of space. If I have negative 1 minus 1, that's the same thing as negative 1 plus negative 1. So it would be a negative 1 subtracting 1, or a negative 1 plus another negative 1, which would be negative 2. If we have something like 1 minus negative 2, that is the same as 1 plus 2. Because if we subtract something, we're moving it backwards. But if I subtract a negative, the negative is moving in the opposite direction. So subtracting a negative is the same as adding. So if I start at 1 and I want to subtract negative, I'll become less negative. So I'm going to become more positive by 2. So this just means become less of this. So 1, become less negative. How many negative places to become less? 2. This is really, really important when you're thinking about adding electrons, which are negative charges. Adding and subtracting electrons is this basic negative math. So pull out a number line if you need to, if that makes you feel more confident in your answer. Put it in the calculator if that makes you feel more comfortable. But be aware that you do need to have a grasp of adding a negative and subtracting a negative in order to contemplate charge of an atom or ion, looking at its electrons, which are negative charges. We will be adding and taking away electrons. There are other things about negative numbers, but I think this is the most important thing, and I'm just trying to give you the most important information here. So if you run into other math basics that you feel like, whoa, I totally forgot that, again, hit up Melissa Maribel's videos. Everything is chemistry oriented with her, or you can come and see me in class or in office hours. Okay, a quick algebra review is next. So first, addition and subtraction. So when we're talking about algebra for introductory level chemistry, if you're in higher level chemistry, I'll make separate videos for the algebra that you need, but for just getting started in chemistry, you basically just need to isolate a single variable. So if I say 3 plus x equals 10, you would need to isolate the x. So as a review of this, if we're adding or subtracting something to the variable we want, we will do the opposite of that operation to the other item to isolate our variable. If I subtract x on both sides, I haven't isolated my variable. I've just moved it and it's still with another number, right? So it's not what I want to do to my variable at this point. It's getting rid of the other stuff next to my variable. So if I want to isolate x, the best thing I can do is, what am I doing to the 3? I'm adding the 3. The 3 is being added. So the opposite of that is subtracting. So let's subtract the 3. And the beautiful thing about equalities is that it doesn't matter what I do to one side. As long as I do the same thing to the other side, it will still be equal. So if I subtract 3 from both sides, 3 minus 3 is going to cancel out. So I'm going to get x equals 7, because 10 minus 3 is 7. And so that's just a basic positive, negative, what to do positive as a negatives for algebra review. If you wind up with something like negative x equals negative 7, we can actually just cancel the negatives from both sides, because I'm not sure if you remember this from your algebra, but what you're really saying here is this is negative 1 times x and negative 1. We can rewrite it like this, right, as times 7. So if we just divide both sides by negative 1, we get x equals 7. So if you wind up with a negative on both sides, you can just get rid of the negative. Speaking of what we just did, let's look at that. If we have multiplication and division. So if I have 5x equals 10, I'm doing really easy stuff here just to show you the basics. What is happening to the x? It's getting multiplied, right? So what's the opposite of multiplication? Division. But we don't want to divide the x. We want to divide the thing that's not x, because we're trying to get x by itself. We're not trying to move the x. We're trying to just get the x by itself right now. So I'm going to divide by 5 to get rid of the thing that's attached to the x, but I have to do it to both sides in order to keep inequality. So 10 divided by 5 is what I'm going to enter in my calculator or do in my head, and I'll get x is equal to 2. I do want to go over with you, though, what happens if you have your x is on the bottom of a fraction. So if I said like 10 over x equals 2. Here, I always get a lot of students frustrated with trying to isolate the x here. There is a trick. You can take the number here and the x and you can switch them. It's kind of like it's essentially a cross multiplication, which we'll talk about later. But you can do that trick where you just switch them, right? X is equal to 10 over 2. Or you can go through the whole algebraic process if you're not comfortable with tricks. What is happening to x right now? It's being divided. But if I divide or multiply both sides by 10, that still doesn't get the x anywhere closer to by itself. When you have an x in the bottom of a fraction, you need to move the x to the top of the fraction. So you can flip the fraction and take the inverse. If we flip this fraction, we flip this, and this is 2 over 1, we make it 1 over 2. A lot of people are probably like, no, what are you doing? Don't do that. Don't make more fractions. Let's just multiply both sides by x, because that is going to cancel the x on this side, and it's going to bring the x to the right side, which is fine. It's just going to take us more steps maybe to solve algebraically. So now I have 10 is equal to 2x. And now I can do what I did before, which is divide both sides by the thing that x is with. It's just rewriting in order to make it more manageable and something that my brain has a better chance of understanding. And that really is the core of a lot of the work you're going to be doing in chemistry as far as the math in chemistry is, okay, let me reprocess this problem or rewrite this in a way that is helpful for my brain to understand what is happening and then solve it. And so I encourage you to go through the process instead of just relying on tricks and tips and things, because it's better for you in the long-term chemistry learning to have a good understanding of the super basics to work your way from very basic to very complicated. Okay. Hang in there with me, almost done. If you have a mix of algebra topics, we're going to use order of operations for that. We're going to do plenty of practices. Use order of operations. The one mix I do want to talk about that we encounter a lot is the distribution method. So distributing. So if I have, I'm using really simple numbers here, 2, 1 minus x, and I want to break this down. We can, if this is equal to something, if this is equal to 10 or whatever, we can definitely solve this in different ways. What I find that a lot of students who are uncomfortable with algebra get messed up on is trying to do it without distributing. So let's just look at, how do you distribute? To distribute, you're going to take the outside and multiply it to the first number inside. So we're going to say 2 times 1 is 2. Now we're going to bring down whatever sign is in here. And then we're going to say 2 times x is 2x. And then we bring down whatever's on the right side. Then we can combine like terms. So the 10 and the 2 are like terms because they don't have x's in them. And we can just do the same thing we've been doing with addition, subtraction, multiplication, division to isolate our x in steps. If you feel like you need more practice with this, if you're looking at this and you're like, I don't know how to solve x, I would say that maybe going to math tutoring to help with basic algebra like this might be helpful. I know Khan Academy is not always great for chemistry, but they do have some pretty good basic math modules for free. So that might be something you want to do to brush up on. But I'm expecting you to be able to solve x from something like this. I'll do it for you really quickly here just to make sure that you got it right. So we will we'll subtract, do both sides by 2. And I have a negative 2x, that's fine. We're going to divide both sides, whoops, not by x, by negative 2. And then our answer will be negative 4. So hopefully you're able to follow along a little bit with that. Again, I'm not a math teacher. I have not certified to teach math, so I may not be the best at it. I can show you, but it's hard for me to explain exactly all of the rules. I'm doing the best that I can to break it down, but there are a lot of other resources on campus that you can use to help you with that if you feel like that is something that you need more review with. And last but not least, let's talk about exponents and scientific notation. So an exponent is just a number that is raised, a number is raised by another number. And it means that how many times you multiply the original number by itself by, which is kind of confusing. So let's look at an example. If I say 2 squared, that is equal to 2 multiplied by 2 times, or 2 instances of that. If I say 2 cubed, it is 3 instances of 2 multiplied together, 3 times. If I say 2 to the 4th, it is 4 instances of 2 multiplied together 4 times. Okay, it's not 2 times 3. It's not 2 times 4. It's 2 times 2, 4 times, if that makes sense. So a lot of times we're going to talk about the exponent with the base of 10. So for example, 10 to the 3 would be 10 times 10 times 10. And when you're doing things with base 10, what's cool is that it actually matches with the metric system and the place values that we talked about earlier. So if I have 1 and I'm going to say, let's multiply it times 10 to the 3, I'll take this 1 and I'm going to move the decimal 1, 2, 3 times to make it bigger, because 10 to the 3 is a big number. And so that would be 1,000. So 10 to the 3 is equal to 1,000. And so this gets us into scientific notation. Negative exponents would be 10 divided by 10 divided by 10 divided by 10, which is really like the best way to write it is this. 1 over 10 times 1 over 10 times 1 over 10. That's the best way to think about it. Divided by 10, divided by 10, divided by. If you were putting in the calculator, you would have whatever number you want. Divided by 10, divided by 10, divided by 10 for -3. So if we have a 1 to the -3, we would start with our 1, and then we're going to go backwards with our decimal 1 to 3 places backwards. So we would get 0.001, because we're making a smaller number because we're dividing it by 10. So a negative exponent means a smaller number. A positive exponent is going to be a bigger number. So something times 10 to the +3 is going to be bigger than that thing. Something times 10 to the -3 is going to be smaller than the thing you started with. In value, smaller and bigger in value is what I mean here. Not smaller and bigger as far as the amount of zeros, as far as the amount of space it takes up on your paper, but smaller or bigger in value, meaning you would like to get a check of $1,000, but you would not really want anything with this much money, right? This is a smaller number of value than 1. I prefer to get $1 than this. I prefer to get this than $1, if that makes sense. So applying that directly to scientific notation, scientific notation has a format, okay? The format is always going to be some number 1 through 9. You can have a decimal if you want to have a decimal, but just some number 1 through 9 times 10 to the n, where n is your exponent. Okay. But the number in front of the times 10 has to be 1 through 9. You can't have 20 times 10 to the n. I mean, you can mathematically in the calculator, but to have correct scientific notation, it's a number 1 through 9. So if I have 1.2 times 10 to the 2, this may seem like a daunting thing to think about that number, but let's turn it into regular notation. So to do that, look at your 1.2 and let's think about the exponent. Is it a bigger number than 1.2 or a smaller number than 1.2? Because this is a positive exponent, it's a bigger number than 1.2. So we're going to move our decimal to make the number bigger. Some of you have been taught move the decimal right if it's positive, move the decimal left if it's negative, but that only works if you're turning it into regular notation or you're turning it out of regular notation, but it's reversed when you're doing the opposite. So I never was able to remember which way was which, so I just learned a bigger number means a positive exponent. So if I need this to be bigger by 2 decimal places, I'm going to take my decimal place and I'm going to increase the number of decimal places by 2. And then wherever you need to fill in, just fill in some zeros. So this is going to be 1, 2, 0. And then my decimal would be on the outside. I'm not going to put a decimal here because it's the incorrect number of significant figures. We'll learn about that in a separate video. But it is 120. So you can write on your paper, the answer is 120, or you can write 1.2 times 10 to the 2. I think it's easier to understand the value of 120, right? So everything doesn't need to be in scientific notation all the time just because you're in a science class. Sometimes the regular notation, like 120, is way easier to understand and communicate than 1.2 times 10 to the 2. Let's look at another example. What if I have 3.02 times 10 to the negative 3? So we'll bring our number down, 3.02. We're going to make it bigger or smaller? We're going to make it smaller. By how many decimal places? 3. So I'm going to grab my decimal and I'm going to make it smaller. To make the decimal smaller, I would move it to the left because 0.3 is smaller than 3, right? So we're going to move it to the left 1, 2, 3 times. And we're just going to fill in these blank spaces. So I'm actually going to write my decimal here. I usually put a 0 in front of the decimal just to make sure we understand that that is the decimal is approaching. It's not just a random mark on my paper. And then we're going to have our 302 here. These are the same number. Now, at some point, you're going to have maybe too many zeros to write it in regular notation. Like this is probably fine. Like if you were to tell somebody, oh, 0.00302. But if I had to communicate a number like this, you're probably not going to say it out loud, 0.000000004. Somebody's going to be like, wait, how many zeros was that? So it's better to do something like this in scientific notation than it is to keep it in regular notation. So how are we going to put it into scientific notation? Well, we know it's going to be the 4 here, and it's going to be times 10 to the something. Well, we need to make sure it fits our format. The format is number 1 through 9 times 10 to the n. Here's our number 1 through 9. The decimal is currently here. So we're going to move it until it's here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I had to move the decimal 10 times to get to where I wanted it to be, where my decimal point was after the 4, so I could have that 1 through 9 as my base. Now, is this number going to be negative 10 or positive 10? This is a number that is very small. Okay, we can think about it as less than 1. it's not a number that I want to get a paycheck for. Keep your money, right? It's very small. So it's going to be a -10. It is smaller than 4. So we're going to make this a -10. Let's do one more example. So if I were to cut you a check for this much, you'd be very excited about that. So would I. But let's say we're trying to communicate this number in a lab, right? If you're trying to write this down a bunch of times in a lab report, or you're trying to convey it in words out loud, it's probably easier. But if you're trying to write it a bunch of times, you're going to miss a 0. And you're going to do math with the wrong number of zeros, or you're going to write it down wrong, or you're going to enter the calculator wrong because you miss a 0 there. So it's really, really, really imperative that we can put numbers into scientific notation quickly if they are a little too cumbersome. Like, these numbers are not so bad. When I start getting a lot of zeros, I don't want to see that in your answers on an exam or a quiz or a lab report. I want you to know when you need to turn it into scientific notation. For me personally, if you have a 4 as your exponent, +4 or -4, you probably need to start turning it into scientific notation. It probably has too many zeros. So 4 is kind of a good cutoff. 3 is understandable. You can usually get away with 3 as not being, too many zeros in the front or in the behind in the end here. But if you have 4, it's probably getting close to deciding to make it scientific notation. So for here, our decimal is currently not present, but it is really here as far as where it would go. Where do I want it? I want it to go in between the 5 and the 6. It cannot go after the 6, because then that gives me a number not between 1 and 9 for my first section. It can be 5.6 here because that fits between 1 and 9, but it can't be 56 because that's greater than 9. So I want to move my decimal so that it's between the 5 and the 6, because 5.6 is in between 1 and 9. And I'm going to move my decimal. I'm going to count as I move it from the right side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I did them both by 10. Okay. That was not intentional, but sure. I'm feeling balanced today. So I'm going to put in my 5.6. We'll talk about if you need to include any of zeros or anything like that when we talk about significant figures later. And we have times 10 to we moved it 10 times. Now, is the number that I have originally bigger than 5.6? Yes. So this is a positive exponent. So that is essentially how to turn scientific notation into regular notation, and how to turn regular notation into scientific notation. There are ways to have your calculator do that for you. So see me if you need some help figuring that out, or find a YouTube video with your specific calculator and have somebody show you if you need. But you can cheat that. You can use your calculator to do it for you. But I do want you to know how to interpret the exponents, and I want you to know how to do it on your own without the calculator as well, because it's just going to be very helpful for you to be able to rationalize, oh, that's 120, right? You don't have to necessarily always go to your calculator for that. Okay, that is all for the math basics and scientific notation video. Thanks for watching.